Thank you so much. Hopefully this will be interesting. This is the first time we are doing this. Okay, so we'll start with the motivation for why we wanted to do this workshop and how it was relevant. And then we'll kind of go over more of the logistical stuff for the workshop. FPGAs, as everybody knows here, are used in many application domains, signal processing, wireless communications, machine learning, networking, etc., etc. There's just too many to really list here. And if you look at FPGA architectures, then mostly, at least they started with very generic architectures because they were supposed to cater to so many of these application domains. However, over time, they have evolved, and modern FPGAs are much more than a collection of LUTs and flip-flops, basically. We started with including larger blocks like DSP slices, block RAMs on FPGAs. Then we've also seen, additions of hardware controllers, I/O controllers like PCIe, DDR, etc., hardware processing systems as well. And generally, FPGA families, like vendors organize FPGAs by size, features, and building block resources. I have these snapshots from AMD and Intel's websites or Altera's websites, showing that how FPGA FPGA families are typically organized. However, with the end of Moore's law, the end of Moore's law basically has started to impact FPGAs as well, and we have been seeing more domain specialization of FPGAs. So we are moving from very generic FPGAs to slightly domain specialized FPGAs. And we see several of them that have already shown up in the last decade or so, probably even longer. For ML, we have the Stratus 10NX from Intel or Altera, the AI ML based devices from AMD or Xilinx. We have smart NIC devices for networking, a lot of special FPGAs with special interesting features for signal processing. We have really like all LUT type of FPGAs for emulation platforms and so on. However, identifying new FPGA architectures for emerging application domains is very challenging, right? It requires us to understand the representative workloads, right? It needs us to analyze performance of workloads and see what the bottlenecks are in current FPGAs, and see what architectures can be proposed that can remove those bottlenecks and potentially serve still a larger swath of an application domain for it to be justifiable. So there is this generality specificity or generality specialization trade-off that has to be looked into whenever we are doing this, coming up with new architectures for new domains. And not just the architecture part, the CAD tool support is super important as well. Right? Without being able to expose the architecture features to the end user, it's very difficult for the end user to take use of these features. So incorporating support for the features in CAD tools is essential as well. So with that in mind, with that importance of domain specialized FPGAs in mind, we decided to do this workshop with the goal of bringing together experts to share knowledge on domain specialized workloads, architectures, and CAD tool algorithms for FPGAs to assist or influence the future FPGA design and programmability. Future domain specialized FPGA design. And before we go ahead any further, I would really like to thank the experts that are going to be joining us today. We have about 10 experts from different fields who are going to be presenting the first part of the workshop, and then there will be a panel discussion in the last part of the workshop. So I really want to thank everybody for doing that. So starting, with some more logistic information, let's just introduce the organizers. We have Abhishek here from AMD. He's the brainchild of the workshop, by the way. I'm just here presenting because I haven't prepared the slide deck. He's the brainchild of the workshop. He, reached out to me and Pally with Andy and hey, let's do this. This is a good idea. And I was like, yes, why not? This sounds amazing. So thank you for kind of bringing that up. And here we are 7 months later. The next is my name. My name is Aman Arora. I'm an assistant professor at ASU. I have been involved with domain specialized FPGAs for a while. Primarily during my PhD, I was working on domain specialized FPGAs for machine learning. Callie is the organizer here as well, but she unfortunately could not join us. She's in Atlanta, just busy and handling other responsibilities at the moment. And then we have Andy from the AMD University program. he has been instrumental in kind of helping us organize this from kind of the very beginning to the very end. All these posters that you're seeing, thanks to Andy being able to manage that and make that happen. All right, so here is the schedule of the workshop. We'll start with presentations. We have 5 presenters, 5 experts. We are planning about 1.5 hours, for that. Maybe a little bit shorter, but we'll see. Then we'll have a poster session in the middle. It's sort of a break, if you will, also to have you guys recharge a little. There will be posters around the room, about 6 or 7 of them. Go and interact with the poster presenters. And then towards the end, we will have a panel discussion. Another set of experts will join us for that. And I'm sure we'll be moderating the panel. And we also have a website. This is a snapshot for the website, and this is the QR code. If you want to just follow along the schedule is on the website. There's a schedule page on the website that you can check. All right, I think with that, sorry, yeah.
Give you one more second.
Yes, please. Okay. All right. So we'll get started with the first part of the workshop, which is the presentations. I will be introducing the speakers, or actually just having them come on here and then present. The themes of the presentations that we have requested from the speakers or the presenters is that they're going to talk about these 4 main things. The experts are from different domains, so they'll talk about the domain that they represent, what applications in that domain do they generally work with FPGAs, and what FPGA features are used, both architecture and CAD features. What limits the performance? So today, when they deploy the applications of their domain on these architectures, on these current FPGA architectures, what bottlenecks do they see? Where are the performance limitations coming from? And then eventually kind of talking about a wish list of FPGA and CAD architecture, FPGA architecture and CAD features, right? What do they want in future domain specialized FPGAs for their domain that will make their life easier? Right, so that's what we are going to have them discuss. And the general, each presentation will be about 12 to 13 minutes, and then followed by 3 to 4 minutes of Q&A from the audience. So please ask questions as you want. We really want it to be a very interactive session, pretty laid back, nothing very informal here. Just please ask questions. Okay, so here is a list of the presenters. This is the order we will go in. Just no real, reason for the order. It's just almost random. James will go first, followed by Tao, followed by Chiru, Philip, and Chris. So I think we can just get started. Actually, I took more than I should have. But James, can you please come here? Actually, I don't have introduction for everybody, so that's my everybody knows James. I guess everybody knows everybody knows.
I'm pretty sure at some point there's 20 minutes. It's okay, I'll go fast.
All right, thank you.
1 second just to get plugged in. Okay, so I'm James. I'm from Carnegie Mellon, and I want to introduce myself. I'll say I've been spending most of my time thinking about how not to use FPGAs like this. And I think for today, I'm more than specializing FPGAs to a domain. I want to find a domain. I want to find a domain that's uniquely FPGA, where FPGA is that's a domain that FPGA should be in. And so the title suggests, right, the thing I've been thinking a lot of time on is this problem called input-dependent irregular string processing. It's a really mouthful, but if you want to just, for example, I think most of you know string matching, not the simple kind, the kind where I give you 10,000 strings. Find me every single one that happens. String matching, regular expressions. And when I say string, what that means is low arithmetic intensity data by 5. You can't hold on to it, you can't store it. I can put it in memory, CPU, GPU will go at it. Right? So these are data on the move. You just have to touch it and let it go. Okay, so that's string. And we know, right, hardware has a tremendous advantage with this kind of thing. Right? We've been building streaming hardware for a long time. This is where the second part comes in, the input dependent, the irregular. Right? By being input dependent, then what needs to happen varies over time. The problem now is, right, most of the time you cannot design for the worst case. Worst case is so expensive and almost never happens. You can't build for that case. Okay? And if you build for a expected worst case, the problem happens is what's expected. Sometimes worse than expected happens. And in that case, your basic becomes very slow or even become useless. And so in that case, I think that this the time varying behavior is what brings in the requirement of what John said, the R part of reconfigure. Right. Reconfigure hardware doesn't mean reconfigure once and become nascent. You need to be thinking of a problem where we actually have to reconfigure over and over again, and then that will create a unique domain opportunity for FPGA. Right. So for FPGAs, I can take a guess at what is the expected worst case, average case, design to that. I can have multiple versions of it, and I can reload if the condition changes over time. And to make this whole picture work out, we do need high-level synthesis. I can't do this on RTL. I need to build IPs and kernels that are very flexible. I can characterize it to different conditions, and I need to have a very convenient way to build out applications like composing them. And lastly, this kind of going to computation, having code that can be maintained and reused is very, very important. Right? You don't want to build RTL that will die when the graduate student leaves. Okay? And if you're interested, I believe so much, I'll show you what I'm doing. So I am working on multi-stream pattern matching. If you want to see what I'm doing, I'll share my GitHub with you. It's MIT license. You can do whatever you want with it. And just give you an idea of what you can expect. Right? High-level synthesis and FPGA are not slow, are not low quality. So one of the things you can find is the multi-stream pattern matching. But what the part is actually not an application. It's a bunch of things you can put together to make what you want. And the one thing you can put together and check out is multi-stream pattern matching. So here I'm taking a particular example because I'm collaborating with somebody else. 60,000 libels, 2 to 8 bytes. And the requirements that this data goes by, find every single one, cannot miss it, and tell me exactly where these are. And there are lots and lots of variations. Okay? But so this is one use of it, but the same repo allows you to build other variations that are all very important. And so this is all done. I happen to be using Altera Sickle, the DPC++ for FPGA. I ran this on an Agile 14. This is like a 2,000-3,000 small FPGA. Okay, I can do 32 bytes per second, checking 60,000 strings, 32 bytes per cycle coming through. I can hit 180 cycles. So this is 128 gigabits per second. And I can actually do more. My FPGA does have better I/O. Right, so here that's 100 gigabits what I'm doing. I'm using actually a fraction of it, 27% block. 30% use. And this is the kind of thing you can do in HOS, you can do on FPGA. And I don't believe you can do better in RT. But this kind of problem, I'll show you a little bit why I believe that. And so in operation, when I do DRAM test, we can actually go over 100 gigabits per second. And we're actually testing in very stressful conditions. And not only we're checking 32 bytes per cycle, I'm generating 2 hits per cycle. You do it the solving of time. Right? You use 680R, HyperScan has a very good pattern matching. You get about 1 gigabit per second per port. So what I can do on FPGA, you need 100 cores. Now the question is, how hard is this? It's not hard. HOS, I can, in this part, HOS is great. So how many people use HOS? No one. Okay, great. For the rest of you, let me teach you the good part of HOS. Okay? So for streaming, this is just for streaming. Both Python and Circle, they have the notion of a string is a native construct. They call a string, they call a pipe, but basically it looks like a Bible. The producer push, the consumer pop. And if you want to write a streaming kernel, it basically looks like this. You have a function. The only input outputs are these pipes, which you can only push, you can pop. That's it. Okay? And as a streaming kernel, this one giant while loop goes on forever. And if you have a stateful string, you can declare variables. And these lists outside a loop, you remember from iteration to iteration to iteration. And then you also have temporary. These just come and go. Those are like light moments. So far, so good, right? It doesn't get much harder. And for each iteration, you pop from the input. At the end, you push in the output. And all the magic happens here. What do you put in? It's a transformation, looking at the state, looking at the current input. What do you put into the output pipe? And generally speaking, you can pretty much put whatever you want in, as long as something can be statically elaborated into the data flow. Right? It flows from inputs to output. Okay, and as long as you stick within this template, then HLS compiler, both Linus and Circle, they can pipeline this very, very well. And so the iteration will be executed in pipeline overlap. If you have state, they will be forwarding across iteration to keep the performance high. And all this, right, this is how I did what I did. Right? So this will get you 480 megahertz or more on a modern FPGA. And kind of what goes into it, I don't want you to think something trivial happens. Right? This multi-string pattern matching, I'm looking at 16,000 string, 32 bytes per cycle. It is not easy, but it's the same basic template. And the way I started, I actually ripped out Hyperscape. I read the Hyperscape paper, I downloaded the repo, I looked at their C code. If you think about this problem, it doesn't matter how elaborate, how intricate the algorithm parallelism is. It is a big data flow graph from input to output. And so in that case, right, what goes into these streaming kernels are exactly those giant functions, big functions. But because these functions ultimately takes input, computes, and output. You stick that in, you run to HOS, it pipelines. The pipeline is perfect. In this case, it is no architectural safety. This is one of the best cases. And so, right, these programs are big, but nice thing is there's C code, the sequential C code, I can debug it. And I did have to optimize a little bit on the baseline, okay, because FPGA is not ADX after all. But it is something that I can debug as a sequential C code, and then I can rely on the compiler to parallelize a concurrency to get speed up for me. I would say this is actually quite pleasant and enjoyable hardware design experience. You should all try it. All right. And that's not even the best part. You know, I build the kernels, but kernel is not an application. You got to put it together. And so, for one thing already, I give you a library of those kernels. That's what a repo is, right? And then you have to put it together. And so we'll put three things together. I have that pipeline, but that's just a pipeline in vacuum. I got to put it in the FPGA. Now comes the part that's scary. Right? The thing that's always scared me the most when design had to go off the chip. Off chip, I need to talk to host memory, I talk to device memory, I talk to the whole CPU. And it's just plumbing. Plumbing shouldn't be hard. And so because I live inside Circle, all this is just part of the language. Right? Memory exists. You read and write memory. There's nothing more you need to know about it. And so if you look inside Circle, mine is very, very similar, right? So I can access host memory either by doing DMA. There is what's called universal share memory. I can do direct load store to the same pointer to the host memory. And also, right, this concept of streaming actually extends out beyond the system. So they are what they call host pipes and IO pipes that will allow me to extend, not just stream between kernels, but actually stream all the way out to talk to other things in the system. And all this isn't some special IP you have to go find out with documentation. It is just part of the language. It's part of the same abstraction. And so now to build an application, this is like scripting CUDA kernels in Python. It is really that level of complication we're talking about. Right? This is something an application person can do. And so here I want to go host mem even the DRAM. I stream in, I stream out. My kernel doesn't understand what data came from. Right? It is at this level, at the main.cpp level, right? The main function is what put together. You know, if I want to redirect from networking, it's just another type. And once I'm connected to the network, my FPGA can be anywhere. Data could be anywhere. Right? It all becomes just abstraction, just part of the language. And so I think this is where, right, there's a valid application, and you know we need to figure out what is the right way to think about the problem and to build, and what a tool can help us. And so here to recap very quickly, right? I begin by offering, I think, input dependent, something that changes over time, and streaming, right? That is, I think, at least a very promising domain for FPGAs. And data analytics is one of the biggest things that happens. It is one of the things that happens in data center. And one thing I hope I convince you is high-level synthesis has come a very, very long way. And it is exactly what we need to create the flexible and dynamic configuration that happens. Actually, the thing I didn't point out is, right, if you want to do partial reconfiguration, that is also partial language. How a kernel, the kernel is not on the FPGA, it gets loaded. You don't need to think about it. There's no reading menu. You write the program, the runtime system make it happen. All right? And part of the exercise of doing this, I really learned to appreciate software engineering. All right? When you build an application, don't just build it once and throw it away. Okay? And so, you know, for one thing, this idea of building kernels, you know, some people like to build high-speed kernels. I'm like that. Then some people know more about applications. They don't need to know the kernels. You know, put it together very easily. And we need to do things in a way where that's actually doable and easy to do. And then IP has to be understandable, have well-defined interfaces, and they can be maintained and reused over a long time. And that's why I hope we start by building that GitHub repo I have. And I really want more people to come play with it. And I don't want to be the only one doing it. And I think the last thing is I don't think I'm actually speaking to the theme, right? You know, what I believe is we need to find the domain, figure out how we're going to program. If we know all that, the architecture, what needs to happen, follows very clear, right? So if you say, with what I'm doing today, right, I can sit here and tell you what I'm looking for, right? But I think it's important before that, picking a very valuable application domain, and then figure out what application needs, what programmer needs. If we can decide that, the rest is actually quite obvious. And I can talk to you offline. Do I have like 2 more minutes of my? Let me see. I don't have. Okay. I want to throw in a bonus, but it's related, but kind of sideways. Okay, there's something very related. So if this has to do with how FPGA and ASIC can coexist and not step on each other's church. And so here I'm showing you. So if you look, we're very used to seeing pictures like this. Right, but you start saying, okay, FPGA is kind of slow. If you really care about performance, have an ASIC on the site to help it. You outflow, you accelerate. And I think one thing to begin to think about, especially in now the chiplet ecosystem, you know, we need to kind of turn things around and think about FPGAs as something where the ASIC can outflow things that doesn't need to be fast, things that are too hard to do next, things like changes over time, right? You can have FPGA be the complexity output for the ASIC. And then here, right, so like FPGA, it sounds like FPGA is going back to being blue logic, but it is a new kind of very powerful blue logic. Right? Now you let the ASIC become very, very simple. And unlike software, right, FPGA can still be part of the high-speed processing data path. You can actually program what happens in the part of the main data path. And so kind of one way, you think of in chiplet environment, you can imagine having FPGA, and FPGA will serve as a much better base than the CPU to support of the ASIC. So that not only you can direct what the ASIC does, you can also be in line of the data movement. So relate what I said about like the research questions. You do not want to program this FPGA in RTO. You do not need to, right? And then once in this traction in this direction, then we can also be thinking about for this class of FPGA, what should it look, right? It wouldn't look like what we have. So I'm glad I got one more slide in, but I'll stop right here. Thank you. Oh, questions, right?
Does anyone have any questions?
Begin at this time.
So these kind of things completes into data solutions. What is it that you see FPGA that can tell you applications?
In architecture. So I think the data movement part, I think NLC, right? Because I have very structured data movement. And one thing that's came lately, actually, just talking to you, right? Part of the if you think about streaming computation, low arithmetic density, what kind of things can you do, right? Lightweight transformations. That's one. And FPGA is very good at it already. The other thing is monitoring or constantly looking at it. And there is, I think, having some content addressable memory. Right? Because if I look at what I'm doing right now, I'm spending a lot of LUTs to out-clutter the fact that I don't have kinks. If you look at if I actually went back and looked at the design I have, all my LUTs went into creating things that looks like kinks. But because I don't have one, I have to be very clever about it. If I just have some kin, it becomes a much simpler process. So I think I think there is something fundamental about pattern matching and streaming and kins. Right? In addition to the kind of lightweight transformation that the bit level manipulation that FPGA is already very good at.
As one thing about any HMS, speak to the experience of what the content curve is like, half page plus, and what that looks like for something.
So, for something stylized like this, just go do it. You take my template, you stick whatever you want in the middle, it will work. Right? More generally speaking more broadly, right? So I think there's the greatest misunderstanding of HOS is where does performance come from? Right? Compiler won't get it for you, right? Even if you write program software, C programs, you have programs, you have high performance programs. The people who write high performance software understand concurrency, understand schedule, understand data flows. And if you are a high performance programmer, you can transition into HOS very easily because you understand where performance comes from and how to get it. Right? If you're starting from Python, then first you need to learn high performance programming. You need to learn performance. Right? And I think the difference is not HOS is just a way to express and for compiler to help you do the dumb things. But you, the designer, have to create a design that have the performance to be extracted. Right? You can't write a Python, you kind of just Python script. Is anyone a Python programmer? Okay, well, so here, so I think it's, you have to be, you do have to be, to get performance, you have to have a need for performance, you have to be aware of it. I think that's actually the more requirement. If you have that, the learning curve is very low. Because more of, I need this. How do I get this? I find it in documentation.
That relates to that question. I'm an RTL designer. How would I translate to HLS? My experience with HLS has been it just wastes my time.
Well, so there, it's kind of, this is the other direction. So, I'm a grumpy old man. So, I, I can write RTL HLS. Anything you can write, I can match it. Yeah. Cycle and fit. And the problem is, if we talk about superscalar output or pipeline, I have to do it in RTL, not because RTL, but because I actually do care about every single bit. What if I do an HOS, I have to say all that. If I have to say all that, why bother to do it? But if you're doing something like this, there's a tremendous amount of automation that can happen. Right? There's a lot more things you don't have to think about. It just happens. And so I think it is the question, right? It's not all RTL are ways of expression. And so kind of and HLS, if I have to say the same amount of information as you plus RTL, then RTL is the word. Okay, so I think kind of understanding so that if slow ramp and streaming is a good sweet spot. That's why I think your entry point to HLS, try this. Try this, right? This get the GitHub first. Right. All of this ultimately look just like this. Okay, no kidding. And then actually, if you look at the repo, there are RTL looking HOS as well. So I'm going to see that for that.
All right. Thank you, James. Let's thank James once again. Also, Chow, Professor Chow from University.
Right. My name is Tao Wei. I'm from Clemson. My background is actually analog circuit design for a long time mixed circuit, mixed single circuit design, a lot of PCB. I was able to, I have 13 minutes. I'll make sure I can finish that. I can look at rehearsing in the mornings. Hope I can do this. All right. The topic, leveraging FPGA technology for accelerating analog circuit design. So I'm going to give 2 examples, which are power electronics design and photonic design. For both examples, I will talk about algorithm, the architecture using FPGA, challenge, and traditionals. First, more motivation. So why do you want to do this? There's this general trend that people are want to use machine learning-based design for all kinds of physical systems to design the system better, including electronic systems, electronic devices. I have an example here. This is in the reinforcement learning framework, but it doesn't have to be. There's so many different ways that you can use machine learning to improve design as well. In this specific example, we have something called agents. You can think that as a machine learning model. And on the right side of the environment, which in this context, it's more like a physical simulator. The way it works is this agent generates a design, send it over to the environment. We call that an action, and the environment will basically simulate that design. After you have the result, you can compute the report and then feed that back into the agent. Then agents can basically design a little better. After doing this for very many times, then you can get a better design. So it's more like feedback system. The way we look at it is from computation perspective is that you have 2 components. On the left side, you do have a machine learning model to train, and on the right side, you have this physical simulation. So as a matter of fact, the grand challenge here is that the training is very slow, and the training is slow not because the speed to train the neural nets. So that part is actually fast. over 99% of the time spent on physical simulation in many examples. So to break this bottleneck, very fast physical simulation is actually required. This includes circuit simulators, electromagnetic simulations, thermodynamics, fluid dynamics, to name it. Well, essentially, all these physical simulators, they are differential equations. It can be partial differential equations or ODEs. We know that FPGAs are great in domain-specific designs. They're very fast. Then the question to ask is that can we leverage FPGAs to speed up physical simulation in these specific domains? And also, the other question we want to ask is that can we leverage a heterogeneous computing platform to combine the best of both worlds? What we're talking about here is sometimes we use general purpose computing to still run a machine learning model. We use the FPGA for the physical simulation accelerator. That way we can kind of like improve speed. The first example, power electronic design. Here, I just pick out this circuitry. This is what we call half-bridge LLC tank DC-DC converter. This topology is being widely used for EV charging station, for the power supplies in the data center. Specifically, the design tasks include we want to have a high conversion efficiency based on low loss over a large range of the load. So you can see that this output impedance will vary. So we in this domain we actually use something called a load like percentage. So we want to achieve a higher efficiency over a range somewhere between 20% to 100%. The circuit topology looks easy, but if you want to maintain this high efficiency over a range, that's becoming a super hard problem. The second one is that we want to have a low the output voltage fluctuation based on the ripples. We want to be able to mitigate those things again over large range. And third thing is the tolerance, component tolerance. What I mean by that is just to think about like if you have electronic big box, you draw like a 10 ohm resistor out of it, the chances that it could be 11 ohm resistor or 9 ohm resistor. So we want to be able to accommodate this tolerance. So we actually leverage this architecture on AWS. On the left side, we basically have this circuit here to run machine learning model, reinforcement learning model, and on the right side, we use the FPGA to do heavy lifting circuit simulation. So on the FPGA part of this circuit simulation algorithm, well, we're not going to the algorithm, but the fundamental is just like piecewise stuff. We have a netlist. Once you build circuit, people with netlist, and we have a Python script to convert that into operations. So a whole bunch of matrix multiplications. Specifically, I just want to go into this equation and hopefully explain the algorithm a little better. So it all comes from this X, and that stands for X is a vector. You have the voltage current of all the nodes, and of course current between the nodes. That's in a vector. N stands for the time in. After this operation, you basically get the xn plus 1, which gives you all the voltage and current at next time step. This is a recursive type of operation. Specifically, it's basically a summation of a lot of the matrix vector multiplication. Some of them are dense, some sparse. More interesting because it's nonlinear circuitry, meaning that the matrix we're talking about here is changing over time. So this is the time-dependent matrix. From compute architecture perspective, it's a whole bunch of systolic array. But the trick is that we have to look at, well, just let me explain this a little bit more. We have this little vector, send them into the array, we get output, and output becomes a new input. This is basically. So a couple of interesting challenges. The first one is that because it's non-linear, you have to basically figure out when to swap your matrix. And also, that actually can be done by FPGA pretty easily, and you can make a little bit like fancy machines to make that happen. You don't have to use a lot of logic resource to make that happen. But the challenge here is really like you have to save a lot of these matrices ahead of time, pre-calculating to save them. So we're hoping that we can leverage all the unchipped memory, and we're currently moving on to HBM, and in the future we like to basically not just simulate a small certain one, have a larger circuitry system, so we wanted more storage space on the chip. So some result, we actually worked with Samsung on this project for a little bit. So they actually helped us to prototype the circuit using this framework, and it turned out that it's better than the best designers. So this figure actually shows that the y-axis is the efficiency, and axis is actually low percentage. The idea is that we want to basically make sure we have a high efficiency over this range of 20% to 50%, and it turns out our efficiency is better than their design. As well, it looks like if this only increase that by 0.5, 0.6% but this is actually considered significantly the same. This is actually used in data centers. The other thing we found that we have another version which is basically using simulation software. It's called PSIM, and leveraging FPGA, we can substantially improve the design speed by roughly 60 times, which is basically. The other example I have is photonic design. So this is really about silicon photonics. These days they're becoming a super hot topic, all because we want higher communication bandwidth between GPU to GPUs. So there are like so many different type of silicon photonic devices we have to design. And specifically the model of silicon photonic devices looks something like that. So I think polarization later. So it's apparently beyond the human experts' capability to design this type of thing. This example is optimal computing. It's an absolute matrix modification. And if you look at the topology here, there's no way that human can design such a thing. We have to use machine learning. The same recipe here is that we want to be able to leverage this architecture. You're still running your machine learning model on the GPUs and the physical simulation on the FPGAs. So design targeting here to manipulate light lower loss. And also we want to be able to accommodate fabrication tolerance. Algorithms for architecture, well, that's figured. This is a methodology equation, changing magnetic field generate electric field, changing electric field generate magnetic field. From like a computational perspective, it discretize the space. Things look like that. You have like this is two-dimensional. Let's look at this cell. We have some physical information here, electric field, magnetic field. To update that from time 0 to time 1, you need the information from its labeling cell according to the equation here, C curl. By looking at that, it's just like image processing. So we can use a line buffer and all these existing techniques to help us to speed that up. For three-dimensional line buffer, we have the layer buffer, the same concept. One interesting thing is, leveraging the FPGAs, we can build these line buffers and to update one cell, per multiple clock cycle, and we're able to pipeline all these numbers to speed that up linearly. On one FPGA board, we did try to leverage FPGA clusters to basically extend this pipeline from one board to any board and be able to achieve linear scale up. Very interesting. So we're using this OCT FPGA platform NSF all out to this project. The challenges we face, the first one is that to build these line buffers, we have to have a lot of on-chip memory. We did leverage the HBM at that time. This was on the U280. But even that, we just don't. We think we need a more HBM for this. The other one is the communication bandwidth. At that time, the one-way bandwidth is only 100 gigabit, not bytes, gigabit per second. We think like if we have a higher bandwidth communication, that would be more efficient. So results, we did take out the chip and show that using this technique, we can substantially. I just cannot give you a number. It depends on the size of the design. Roughly, like 2 hours, 3 hours, maybe faster than what we can do on ANSYS numerical, which is conversion software. We're pretty happy about the result, and we have some friends help us to take out these designs, some testing, pretty good results. To summarize, model designs needs machine learning. bottleneck is not machine learning training on the neural nets. Bottleneck is actually physical simulation speed. And those specific design on FPGAs may play a role to accelerate the pace of physical innovation. Thank you. I'd like to thank the invitation, Armin and the committee, sponsor, students, colleagues, and specifically at FPGA cluster. We actually use that for free. This is the OCT FPGA platform. This is just a free resource. So I think the Mirror research team at Northeastern University in Boston. Thank you.
Do you have any questions?
Oh, in those cases, we use HLS. Since you mentioned that, I actually learned the HLS from this. Then you can know the existence of it into not too long. But for this part, the communication part, we use a UTP, and that one was done in just this module for communication.
And then add on, so you mentioned sort of needing more HBM. Are there any other FPGA features that you think you
Two things, which is on the slide. One is one or more for memory. HBM is terrific, and the communication bandwidth. And currently, I think like internally they're using these cluster cables, high-speed cluster cables for communication, 100 gigabit per second one way. So it's a two-way communication. We're hoping. We think like if we can improve that from 100 to 200, that will speed up significantly.
So for the FPGA, that would be like more transceivers or something. I mean, like this communication is between FPGA and like probably two FPGAs, I guess, right?
Yes. In this cluster, this is done using a switch, but yeah, you can do peer to peer. We didn't buy any FPGA boards, so we don't know. We have their experience about that. But this is platform again. Like, it's pretty good. I would highly recommend. It's all free. OCT FPGA. You can check that out.
On that, I was actually curious. The end that you have is your simulation part actually also underneath it with that?
Yes.
Not all smoke, but
So if for bandwidth, I'm talking about communication bandwidth between the FPGAs or the bandwidth.
like I'm curious between the two. Which one? So
Between the two, HBM. We need a more bandwidth, like a fast on-chip memory. Yeah, just for this specific application, you just need to build these line buffers, and these line buffers in three-dimensional space, those are large. So we want to definitely more HBM use.
So I get it as a whole, are you able to what percentage of it are you
The percentage of the percentage of the bandwidth. Well, we're pretty much like again, like if we're talking about the communication bandwidth already saturated, so we have to kind of wait so that's why bandwidth will be helping the overall speed tremendously.
Yeah, one more question. So you mentioned that you power supply design and produce designs that are more efficient than the best power supply designers that we have humanly. So my question was, do these designs maintain the same kind of reliability? Because I understand that for like high HPC like applications and servers and that stuff, you usually want as much uptime as possible.
Absolutely, yeah. So for that part, I figured out things work from the universities doing university lab on top of research. But our collaborator at Samsung, so they do have all kinds of different verification techniques. So they did a prototype to guess that it's pretty reliable. And this is just in the beginning. This process is sponsored by Naval Research. We're hoping to keep building a larger all kinds of different systems to see.
All right, thank you very much. Thank you, Tao. Let's thank the speakers. Next is you, Professor Jiu Zhang, for now. I guess we are adding a question that everybody has to answer. What are they using it to support? Yeah. Thank you, James, for setting the thing out of the answer. Yeah, this one's easy.
Great. Thank you. So member from Cornell. I'm also on the augmented community of research conference. So thanks for sticking around on Saturday. Thanks for talk. Today I'm going to talk about some more recent effort on computing power. So power is a good model for something called the data activation. This is the term that I'm going to take research. I actually believe that the context of this case is well understood by the audience here. We are in this era of data explosion. The emerging applications are growing data intensive. And they're big for sure, and they're becoming sparse, very dynamic, and also private. And also, you look at the current power, so they're becoming more continuous. So whether it's within the device or cross device, they are the data movements are actually pretty expensive. So that's where you argue that really important to special data to meet these evolving demands of both application and also power. And so that's where you need possible. So we really want to use smaller, simpler, and sparse data, and also do data locally and directly if possible. So again, to explain this notion and data, so here's the taxonomy. In my mind, there are three key aspects. Okay, first is the numeric type. So this is basically where we play the trade-off between the accuracy and the efficiency. So these days, there are actually a wide range of different database being explored, especially in the ML domains. There are all sorts of low Lewis statistics that are being explored, and I think it's also looking into some of this. Also, we build a very low Lewis neural network server on the FPGA before. And the second one is data format. And so that's where I'm actually covering both the data structure, the logical data structure, and also the physical layout. Actually, for many applications, it's extremely important to exploit this sparsity. Okay, so that's where actually there are a wide range of data format to also consider. And last but not least, we also want to optimize the data flow across the memory hierarchy, storage hierarchy, and over here. So by data flow, I mean both the data location, the data placement, and also the data. Okay, so in the interest time, so today I'm gonna just cover two aspects very quickly. Some of recent work in these areas. So I'm going to talk about the data format first. So that's where we are looking at some of these sparse linear algebra workflow, and we are trying to leverage this HBM equipped FPGA to speed up this workflow. It's actually very memory bound application. So specifically, we looked at graph plus. So this is basic formulation where we actually use linear algebra, sparse linear algebra operators to represent and to capture some of these key graph processing algorithms. We built graph logic, so we published 2 years ago, ISFPGA25. Their interface is a graph plus framework, and directly map it to HBM in this LV FPGA. We also built several highly optimized kernels, HLS, for both sparse matrix, sparse vector computation, also sparse dense vector computations. Actually, all the codes source. Actually, the results back then are truly encouraging. So again, back then, a few years ago, we basically compare it's a 16 nanometer FPGA, Alveo, right? This 16 nanometer GPU and 40 nanometer CPU. We are actually getting better performance across the board, right? Compared to some of the state of the art framework back then, like running CPU, Droplet, well, plus running GPU, and also some other FPGA server for graph processing. and they're getting higher performance throughput. Also, more importantly, actually, even with the older generation GPU, so you look at the bandwidth, still much higher than LPU. But we are actually, and this is actually memory block application is a sparse workload. But we are still able to get much better performance, right, in many cases because achieve much higher bandwidth efficiency in bandwidth utilization. In terms of in this case, the unit is the median, the end is reversed over the bandwidth. So the key thing, one of the key ingredients to get this performance, to get the bandwidth efficiency is that we actually customize the sparse data format, the matrix format, so that we actually matches make the data in the HBM, the data layout, match the parallel speed of the observer itself. So that's where we can actually avoid, instead of using the traditional format like CSR, where we have to deal with this more random and also non-streaming accesses, we are able to actually get away with a more customized format and get much higher with streaming access from HBM. And we actually try to avoid it as much as we can. Actually, these days, there are actually wide range of different customized formats sort of popping up, right, for different kind of servers, not just for FPGA servers, and also for ASIC, and also for GPUs. Actually, whole zoo of different kind of customized format being explored. So this actually motivates us to look at this whole space. And we're actually looking at how to unify the representation of these different kind of customized formats, not just traditional formats like CSR or COO. We actually come out with a fairly elegant way to unify the entire space of this sparse format. We come out with a tree-based representation and also come out with a language-based representation using MIR. We developed compiler for backend, the CPU, GPU, also coming in memory backend. We are actually working on an FPGA backend so that hopefully we don't even have to write HOS code. Actually, write HOS code for sparse linear kernels stuff that pleasant. Again, this is also open source. It's completely sparse. It's published in one of the top language courses. And next, I also want to cover our work on data flow. So in this case, I want to go back to a dense workflow. This is the one that everyone is hearing about these days, right? LN. So really the question we ask is, can FPGA even compete, right, with GPU for LN inference in some aspect, right? So this may seem like a silly question, right, given how GPUs are dominant, how dominant GPUs are, right, in the current market space. But I think it's still useful to do an academic study, right, just to understand the limit and make the gap. Right? So we basically went ahead with the study, right? We actually come out with an analytical model to analyze the throughput, right, the bandwidth efficiency. But specifically, what we analyze is we are looking at this as sort of model-specific data flow. So instead of building something more or less generic that can run any LM models, so we are looking at can we build this is actually what we just looked at. Can we build something more special, which is model specific? And also we want to make use of streaming, like what James mentioned, as much as we can. We minimize the option memory accesses. This is published a year ago at FCCN. Trust. So this is the funding, right? Not too surprisingly, right? So for LM, there are two stages. The first stage is not pre-built, right? That's where we process and count. So it's actually compute done. Okay? So that's where it's really hard to compete this GPU because we don't have that many multipliers right, on the FPGA. And this is also what we found based on analytical model. But the nice thing is actually in another, in many cases, more important stage, the decode stage, is the algorithm stage. So that's where we actually have a chance based on our model. Even this actually more memory up to this stage. So that's where we don't need that many. So we don't need that many multipliers. M here means the number of multipliers that we run concurrently per cycle. We don't need that many to match the performance of Actually, in this case, A100, very recent GPU. So we are looking at LPs. Okay. So then we are encouraged by this analysis. Basically, when you have to review the example. In this case, we are not even using HLS. We are actually using something at higher level. So we are using something that my group developed as an actually Python-based model, that Allo. It's also open source. It's like I said, the higher level. So this allows us to better interface with the higher level DSL like PyTorch. So we import the model. So with Allo, we can actually quickly build fairly complex systolic arrays just using a few lines of Python code. In this case, actually just write it in Allo by just adding a few set of primitives in a decoupled way. You can build output scenery or wasted or different types of storage, and also put them up and compose it very easily. So this allows us to build a complex and realistic model-specific server. In this case, we got GPT-2, so that was the only open source model from the GPT family. We put that on LU, 16 nanometer. Again, so we compare that with A100, 7 nanometer, and this is model specific. Actually, every single artifact over here, this little thing is a systolic array. It's not a DSP. So we have basically, we are doing the screening access is actually key to get high performance, also minimize the energy consumption. Okay? So otherwise, we have to go back to the HBM and so on. Okay? Also, we are using heavy cache. It's not like it's actually fully. So the results are also interesting as it actually gets speed up. Also, compared to other state-of-the-art object servers, and also we can speed up over GPU, highly optimized GPU execution in the default stage for this model. And also we are more energy efficient. And the whole thing is built in a few hundred lines. It's supported in a few hundred lines. Okay, so just to summarize, I mentioned this notion of data specialization, right? I think this is really key to get high performance, also high efficiency for domestic computing. And look at this Octavian space, right? This product, and there are a lot of interesting research opportunities. And I think with FPGA, it's a unique target to achieve, to realize data specialized servers, and could become an ideal one when you can actually have. It would be always nice to have higher bandwidth and memory, and also we want to think hard about how to be customize function memory hierarchy and get a high bandwidth efficiency. I think that's really key. Because you look at the example that I showed, even though the GPU is much less bandwidth, with the peak bandwidth, you're still able to compete in many cases. So the key is the utilization. And also tooling support. Right? So I really think that we need to support high-level DSL, and this may sound like a pipe dream, a mid-scale system generation, but I recently supported go to pursue this analysis for data flow accelerators. Actually, we have a full papers actually use tools as well, rapid right in and rather that we show that if you just focus on data flow style accelerators, it's actually possible to decompose them and also run case route in parallel and to get high speed in terms of data the research. So please that.
Thank you. Any questions?
I'm just curious about the how the effect of platforms from on the future. The other question is how do you handle TV action?
Right, great question. Right, so see the first question about quantization. So that's where it's really important that we use higher level DSL. That's why we went with Allo. Because that's where we can easily interface with the silent model, very actually and parse some of those quantized, whether we are putting information or there to do the processing more easy and even for those things, for those types. And for KB cache, we basically put that up. each year. And I don't think there are any restrictions in our model that we actually apply additional operation on leading hash, so we can also support that.
Here's a question. So in Allo, is there design space exploration that is happening also, or is it mostly just going to be just
Right. So for this one, for this GPT-2, we basically wrote 50 lines of object improvements. Not too bad, but we are adding automatic ESC support. So obviously have and the GPU. So this would be even more of
What do you think would be the
sorry.
the
Right. So like I mentioned, right, so I think this is also what James stressed. Right, so it's over here. We are basically doing this sort of derepresentation right, between the kernels. So it's more GPUs. Right? We don't have a launch kernel. We load from the memory HBM or other places, right? And do that switching in parallel, and then put it back. So over here, many of these computations happen just through these very small cycles. That's where we have but these are even GPU are adding data flows. Right. So in this case, again, seems like there is a place to compete at least. In this case, actually, the low batch settings. Right. So there is a chance to get almost high performance, high efficiency. The key thing is that we are implementing model specific architecture. This is highly customized. But there are actually many other systems we do not do like RCD. In this case, we are just basically using the sort of standard quantization, that's even lower these days in some cases. So that's where I mentioned like so going from high level with ESL to this string, make that pass as smooth as possible. That's what it is.
Okay, and thanks actually once again. Next is Philip, Professor Philip Leong from University of Sydney.
Okay, good morning, and thanks so much for this opportunity to talk about domain-specific Okay, sorry about that. So I'm going to talk about radio frequency machine learning. I've been using FPGAs for a long time, and I've always said the solution looking for the right problem, and I think that radio frequency machine learning could be the right problem. And the kinds of things that we want to do are that we have high-speed data. On an FPGA can have 16 4 gigabit per second analog to digital converter inputs. Apart from taking the data in through the ADC dump here, throwing it away, what else can you actually do? And what I want to propose is this little high-speed processing block. And its goal is to take the data and reduce the data rate so that we can process it in a conventional fashion at a reduced rate, which is either slow enough to deal with it continuously, or that it can filter so that the red part only needs to deal with intermittent, interesting data. And an application for this could be on satellites, where the bandwidth to the ground station is not very high, and we want to basically only deal with interesting things. So the domain that I want to address is how can we improve architectures for radio frequency machine learning. And there are many applications. I guess the most widespread one is probably 6G, but in radio astronomy, cognitive radio, lots of such things. We've been studying something which is called cyclostationary signal processing. I think it's a really good pre-processing step for machine learning. And the introduction is probably a 30-week course, but I'll give it to you in 30 seconds. What we want to do is that if we have a signal that changes in time and frequency, we take a center frequency F, and we take a span which is A in frequency around it, so that it's plus A12 and minus A12, and then we correlate it. And what this does is that it reveals things like, say, the simplest case, frequency shift keying, where I have data that changes between the two frequencies. If I can put F at the center of it, then all the outputs will be 0 in this plot, except for when I get it just right, there'll be a peak at that point. And I can use this to understand things like modulation types and all this. And I can do it for signals that are well below the noise limit, minus 20, minus 50 dB noise limit. And actually, as an aside, we've developed a fast algorithm to do this, which is much better than nlog-n, using an idea from MIT for this sparse FFT. So in my example, we're going to use this as features to machine learning. So as we know, modern FPGAs now have these high-speed data converters, and they actually also have some front-end processing, like for error correction and down conversion and other things. And the reason that those blocks are there is that you just can't do it unless you have these as hard blocks, because the data rate is so high. And this has often opened up new opportunities in quantum applications, test and measurement, and radio. And we haven't really started using machine learning on these problems because the data rates are so high. So I think there are two problems that can be addressed with domain-specific hardware, so modifications to the feature architecture. So the main issue is the data rate, right? If the data rate was slow, we wouldn't have a problem talking about it. So that's one thing that I'm going to talk about. And the second one is power consumption. So, the data rates, as previous speakers have already said, we can be dealing with 10 gigabits per second or 100 gigabit per second type data rates, and we could have multiple channels. And for radio applications, the data is in IQ squares, which are complex numbers, not here. 12 to 16 bits typically. And our FPGA really only deals with low clock frequencies. James is saying 400 megahertz. That's pretty high for an FPGA design, right? But we're talking much higher data rates than that. And so the way that we normally deal with this is coarse grain blocks. So the DSP58 or 48 is a very low level primitive. It's a multiplier in an adder. And I think that we need to raise the level of abstraction with this so that we can be sending it something, and then there'll be a program inside it that can process the data at a high, hopefully we'll be at a gigahertz or higher, not the kinds of typical frequencies we deal with FPGAs. To be able to do this, we need local memory, and also a keyword that share with James's stream, I think that the input and outputs need to be streamed. For radio applications, it'd be nice if we could deal with complex numbers, and the fabric should not be bit-based like in a lookup table, but it should be word-based. And then we can achieve high frequency. So if you think about it, actually the AI engine has many of these features. I might argue that the block is a bit too big for for this type of application, but it's actually very nice. It's not bad to program, etc. And another thing which featured in the FPGA conference are these flatnets. So they can achieve really high data rates and low latency. I think they're very compatible with radio frequency machine learning. However, the kinds of problems that we're solving are not image learning. They're kind of really small benchmarks. And one observation is that the accuracy that you can achieve with flatnets is compromised by the sparsity. We ideally would like any input to neuron to be at most 6, right? Because we use 6 input lookup tables. So a compute block that's more suitable for radio frequency machine learning would be able to support a large fan-in, which could be done by streaming data, maybe ignoring some of the inputs or just using a knob or something so that we only get the data that's relevant to this particular neuron. And then again, it should be word-based and it should have a high level of abstraction. Power consumption. So in the AMD chips, the ADC is built on the chip, which is really nice. I should have taken a different approach with the Agilix in that they're using chiplets. So that provides an opportunity to customize the versions. So if I'm doing sub-gigahertz radio stuff, then I could be using a different chiplet to, if I was going for the maximum data, etc. So I think chiplets are a very powerful idea and could be used in this domain. And integration is always good because it reduces data movement and that saves on power. And when I'm talking about power, one thing that I didn't realize when we started this work is you run the Vivado tools ad, and it comes back, it says power consumption is 6 watts. So I think, oh, great. I can make a device that's give it 10 watts up and I'll just sell, no problem. However, if you actually measure the power consumption on the system power consumption, board like the ZCU111 is using, well, the lowest we got was about 35 watts idle. So just running Linux and one data converter. So that's something which needs to be addressed as well. So hopefully I've set up the problem, and I'd like to propose to talk about a hard block that we're working on. And this is a DSP and ENN hard block. So in our problem, we want to do cyclostationary analysis, and we want to do lots of FFTs. Actually, I didn't talk about the dimensions of it. That figure that I showed you right at the start, we want 64 by 1 million or 2 million. And we want to do that for every single network. So we need to have an engine that can do FFTs. And an architecture that we came up with is basically a butterfly processor, but you can swap the trickle factors with arbitrary weights and make a neural network. So this idea of the butterfly processor came from Imperial Samsung. So, a couple of years ago, but we've been working with them using this idea so that our hard block, our proposed hard block can, combine an FFT and this butterfly network and do it really efficiently. Students working on it, and I'm told that you'll be all debugged next week, but she's been signed up for quite a few months. So what can we use this all for? Well, here's an example of something that we can't do, which I'd really like to be able to do on single FPGA, which is RFC understanding. So in this room, probably everybody has a mobile phone in their pocket, and there are a bunch of computers, mouse, mice, Bluetooth devices, etc. Imagine that I had a beamforming system, directional antenna. It could basically localize all of the radio sources in this room. And then it could do modulation classification. It could work out what kind of device that was. And it would use the psychostationary processing and stuff. And then it would do machine learning. If I knew that I could associate Ryan's phone with a radio frequency fingerprint, I would actually even be able to identify, oh, that's Ryan's phone. And you could imagine, just like we could do scene understanding for video, we could do scene understanding for radio. And then we could maybe use augmented reality glasses that could give a display which superimposes the video with the radio frequencies. So to summarize, in radio applications, you always need more speed. You want to basically cover the whole spectrum if you can. And domain-specific architectures could improve high-speed processing. I think that probably with one new hard block that can move DSP and deep neural network to a high level of abstraction, it would improve programming, improve productivity. And I think the keys are that it needs to be programmable at a high top frequency, use local memory, have the right arithmetic, and be well based. I think that we need streaming interfaces and heterogeneous programming too. So the two questions that I'm pondering is, can these blocks be generalized from radio signals to any high-speed data sets? It could be a network interface or a wide network interface or something else. And how would the blocks be a bit different? And then, do we really want a hard block, or should it be a chiplet? And then, or maybe both, but perhaps options. Thank you very much.
I'm just going to answer the first question. All right. Does anybody have any questions for Bert? Oh.
So at one point you point to frequencies. Sorry. I understand. So when you said is it a rate, or there's actually a loop in your communication deep and deeper?
Oh, yeah. So I wasn't clear, but I just think that if we're not operating at gigahertz top rates, then we're leaving a lot on the table, because if you can go from, if I have an HMS design that's within 250, okay, sure, I can use, if I can operate it at a gigahertz, then I'm going to be able to do 4 times more.
So we should follow up.
Yeah.
After this side, the HOS and FPGA side. And so one thing is, so there are parts of FPGA that is gigahertz, right? And then one thing we do a lot is 500 megahertz and twice as wide, right? And so if it's a rate thing, then ways to make it work. So that's small up.
So let's have a chat on the decision.
You mentioned that at some point you mentioned that one of the populations was set
that if target state of 6 blocks, actually we are expecting.
It's the so sorry if I wasn't clear. The 6 blocks is the FPGA consumption, and the 35 is everything else. So yeah, it's not the FPGA; it's everything else.
Can you comment on the latency sort of constraints that you have in your applications? So,
Yeah. So it depends on the application, of course. In some applications like surveillance or monitoring, if you're on a satellite, then the latency is not crucial. But in applications like cognitive radio, you better have very low latency, or else of course with voltage.
and how does that get into getting into AI instances of those sort of things? Have you had any issues with links trying to use those accelerators or those sort of applications?
Yeah, so I mean, if you need to deal with high data rates and achieve low latency, then the only thing you can compromise is accuracy, right? But we have made applications where we try to minimize the latency, and I think that these LUTnets, etc., give you the opportunity to really reduce the latency at the expense of accuracy.
Great. Thank you for that. And we have the last presentation, Chris from AMD, Dr. Chris Levin. He's going to give us the CAD side of the view of these stories. So, just.
All right, yeah. So I'm hopefully I come from the CAD side. So what really interests me is getting place and route, getting to a bit stream, getting that really fast. I really appreciate all the work that's been shared today. And Zero pointed out, that it's not a pipe dream. I think we really should push towards getting to the bit stream really fast, like on the order of seconds, maybe single digit minutes. I don't have anything to talk about today, but we have some exciting, promising projects going on. You can come talk to me after about that. But today, I think we want to stick with the task at hand, or the theme for this workshop is, from a CAD perspective, can we exploit domain-specific attributes with the FPGA tooling, right? Just today, I want to take a look at 2 different domains. So a couple of different domains. So we have AI and ML, that's a pretty popular one, and then emulation and prototyping. These are 2 very interesting ones because if we look at the characteristics of these different domains, right? If you look at AI and ML, right? Typically what you'll find in the design are highly replicated kernels, right? You're doing lots of matrix type computations, and you've got to do a lot of it at once. So you've got these kernels that get replicated. Very interesting that FPGAs are really great because typically we want to optimize the data types for these applications, and FPGAs are just probably the best architecture to optimize for that varying data types that come through your application. And typically you're trying to get really high performance, so you're more tolerant of the compile times. You're willing to spend that extra time to get a really good result. Now on the emulation side, you've got very different design goals, right? So you're typically running your designs single digit, maybe 10, 15 megahertz at the most. So you're really not pushing QR very hard. And you've got racks and racks of these FPGAs, so you've got lots of area. So you're what you're really going after is faster compile times, because you want to get to the point where you verified, you validated your circuits, and you want to compile that as quickly as possible. So we're going to talk about these two different domains. So let's talk about AIML, right? So if we consider a kernel, right? You've got a kernel in your design. Let's say it takes 32 DSPs, about a dozen block RAMs, 1,000 LUTs, 100 flops, right? If we target the V80 device, let's say our application, it's going to require 170 copies of this kernel to meet the bandwidth requirements, the latency requirements. Well, how do I create, I write this up in either RTL or HLS, and I compile it. And, Vivado, does a pretty decent job, right? 505 megahertz, that's not bad. It took about 70 minutes to compute this array of computational elements. But, question is, can we do better, right? Let's exploit this characteristic of, hey, I've got this highly replicated circuit. So if I, take one copy of these kernels and I find like the best spot in the fabric where I can put this thing, right? So everything's very close and compacted. I put an area constrained P-block. Other than that, I can get up to 725 megahertz. It only takes 10 minutes to compile that. Okay. Now I ran like maybe a couple dozen different builds in parallel, but I just picked the best one. Well, now I've got this really fast instance. We can use a tool like RapidWrite. So RapidWrite is one of the tools we work with. It's an open source tool. It has this ability to take a place around circuit and translate it, copy and paste it across the fabric. So we identify this block, and now we can copy and paste that thing all the way across fabric, leveraging the inherent replicability of the fabric, the homogeneous nature of the fabric, and we can get up to 688 megahertz. And it only takes us like a minute, right, to take that single instance, replicate it out, build out this array, and we get 36, QR improvement by doing that. And so this is a strategy that, when we can take advantage of these applications. So this won't work for every domain, but it works for this domain. And it's something that we really want to try to exploit by enabling it through the CAD tools, giving you those capabilities so we can leverage them. Okay, now, what do we learn from this? So the Alveo V8 is a very nice architecture. But can we make it better? Like, what can we do to this fabric to improve its ability in this application? Well, we recognize that there's, in this case, the kernel, we could find 9 instances where it gets copied and pasted across the fabric. Okay, that's because the way the DSP and the block diagram columns line up, we get 9 different copies. But if we take the same DNA, the same area of that fabric, we rearrange the columns to maximize that pattern, we can get 33% improvement. So we're going from 9 copies to 12 copies. So you've increased the potential bandwidth of utilizing this technique just by rearranging the silicon. So we didn't have to spend more silicon, we just had to rearrange it. So this is something that's, we want to advocate for, make the fabric as homogeneous as possible, or that the patterns that occur within the fabric as repetitive as possible. Okay, so that's AIML. So let's switch over to English and prototyping. One of the applications in this domain, specifically, are ECOs, so they're engineering change orders. So you've got your big, gigantic design, it's placed around it, you already finished timing, you're like, oh, I got a bug, I got to figure out what's going on here. So you need to go in and make a change. You need to say, I need to look at that signal right there, and, so that means I got to change the place of route. And so that becomes, a task you need to do. Well, the design only runs at like 10 megahertz. I've got to route this thing, and very small number of changes I need to look at. It's like less than 5% of the routes, maybe even less, 1%, depending on what you're doing. So, Vivado actually has a special ECO routing mode that's faster than the general mode for this specific application, right? And it, varies between 20, 30 minutes based on the number of ECO routes that you have to route. Well, Vivado is a generic tool. It has to satisfy the demands of all of everybody's domains, right? And even though you've optimized it for this specific task, it's built for general purpose solutions. So can we do better, right? So if we take RapidWrite, we have an open source router inside of RapidWrite called RW Route, and we can customize that router specifically for this domain. Last year at FPGA, we had this routing contest. We said, if you pull out all the stops, how fast can you route on an FPGA, right? If you just ignore timing, just try to make it as fast as possible, just get a valid solution out of your router. We've actually incorporated some of the solutions from last year's contest into RW Route today. Not reflected in these rows, but because we're only looking at 10 megahertz designs, closing timing isn't really hard. Like you don't have to try. So we can skip the running timing report and all that kind of stuff. We just route the design. So with a ECO specific open source router in RapidWrite, we can get like 25x. So instead of taking 20, 30 minutes, routing these ECOs, we can do it in like 1 minute, 2 minutes, maybe 3 minutes, and we get like a 25x speed up. So these are opportunities for us to identify specific characteristics of our domains and optimize the tools for that specific task, right? And the vendor tools, typically, they have to do the heavy lifting for everybody. So all the domains, they have to satisfy all the needs there. But with open source tools, we can optimize for these specific applications, right? So how is this routing faster? With RW Route, we can increase the parallelism. We can leverage some of the. So RapidWrite is in Java, so we can actually leverage a lot of the parallel data structures, current data structures that allow us to do lots of things that makes it very easy to parallelize. We can make the router faster to initialize, right? So Vivado has to initialize for every potential use case that could ever be thrown at it. And in RW Route, we can just say, hey, we're this ECO router. We don't need to load all this other stuff. We just optimize for the case at hand. And there's during routing, sometimes you have to rip up routes. If you spend all your time ripping up the routes and then trying to reroute everything, because you're trying to meet some timing goal, that takes longer. But when you just need to get a valid routing solution, we can be very selective about how we rip up. So we just only rip up what's precisely necessary, and then that allows us to find a solution much quicker. For example, in Vivado, it typically will not explore LUT route throughs to find paths because they typically incur a much higher timing delay. But in this case, it doesn't matter. You can write through, and you get much greater routing flexibility by leveraging that technique. Okay, so what do we take away from here? Domain-specific CAD tools will unlock a lot of potential, right? We can get much better QR, order of magnitude or more in compile time. When we're building our FPGAs, we want to make things as homogeneous as possible, identify those patterns that occur, make them easier to use. Obviously, looking at how we can make our FPGAs more amenable to even broader data type, quantized data types. And, really open source CAD tools is really going to be the way to go. I think we've got all our own domains, but when we identify what those specific capabilities and attributes are in our domains that we can leverage, we can put them out there in open source and people can share, and we can accelerate that ability to take advantage of those things. So RapidWrite is out there. It's an open source tool. We're happy to help anyone who's interested in leveraging it. And yeah, I appreciate the time. Thank you.
Do you have questions for Chris?
So if you're using RapidWrite in that mode where you replicate the module of the chip, is it tricky to deal with data distribution at first?
Yeah, so there's lots of techniques we employ, right? Because if you place it around something in a box, you can get yourself into a pickle because then, like, oh, I need to route into the signal, and you won't get there because you crammed all the routing in one spot. So we actually have some techniques where we'll attach flops outside of all peripheral connections and put those outside of the B block. And so that guarantees that there's at least one route into those series. So we'll trim off all those flops in the external routes, and then we'll go ahead and replicate it. So that's a good point. And obviously, it's not magic, right? You do have to put some effort into your RTL design, your HLS, right? You design your design in a way that will implement well. RapidWrite's not going to fix it. You have to do well-designed approaches.
So much. You go back to the regular price average slide. So better look. The one where you. Yes. Okay. I just want so this is very interesting. So I just trying to figure out what's keeping you from like concretely this picture, what's keeping you from making it completely regular and going forward, right? So if we make this regular fabric a first class argument, right, how much more does that cost us? And what's you think about granularity? How big should these things be to be repeatable or help?
Right. I mean, that's a great question. And I think, there's all sorts of design requirements that go into what goes into a fabric. And to be honest, prior architectures were not as good as the V8, right? We used to have, slice L, slice M's, and in V8 or in the immersive architecture, they standardized, okay, it's 50-50. Everywhere is 50-50. So you're always going to see, if you got a slice M, it's always going to be the same relationship to the slice L. So there have been changes evolving over time in this direction. But I'm saying, like you said, we want to make it as first-class citizen, make it as homogeneous as possible. There's lots of things nowadays, right? And so you have like the knock, and you have to put the knock in there, and there are probably design requirements about how the knock gets implemented. PCI Express, cores, and all those things that they still need to be in the FPGA, and you can only put so much on the periphery. So there's a lot of design requirements. I'm not probably the right person to answer about why AMD does things in a specific way.
On a compiler side, do you want that to be very regular Chinese scale or make the figure?
I would say both, right? You want to look at every level, and at some level, it's going to repeat it in a small, fine-grained pattern, and then when you level up, you want to see patterns at a higher level as well. Thank you.
Actually, so looking at the change that actually got made, really is columns out. I was wondering, does the direction of the touching matter in this case, right? So you have DSP rail, and DSP knock. Right? So you have like what's moved is around to DSP up if I'm reading this left to right. kind of route your direction.
Yeah.
Like, so you got this, the pairing for this specific application, this DSP rail, left to right. Right, I could imagine an application that would need the other pairing.
Yeah, so for this application, and I think in most applications, whether the DSP was on the left or the right of the block diagram, I don't think it matters. So what you want is you say, oh, I need a column of DSP, I need a column of VRAM, and I need like 3 CLV columns, right? And so if those occur in any order, it's fine. Like I think that, I mean, there's probably like little nuances in terms of, if I'm trying to eke up like, if I'm trying to get 770 megahertz versus 800 megahertz, maybe that starts to matter. But I think in this case, we found the pattern that occurs most frequently in this fabric is that, okay, we're going with this one because this is happening 9 times. We actually have tools in RapidWrite that can help you analyze and identify here's the patterns that occur most frequently, and then it'll prioritize and give you a list. So, I mean, that's a good question. How much, at some level, we have to tape out for somebody, and but yeah, so those patterns, the mix is probably more important than the exact.
Yeah, if you look at overscale plots, left and right connectivity, property of plots. Now that said, you can arrange things in such a way you create unequal container. I just put slot. You arrange things on the surface to create unequal dimensions. So
Awesome, thank you. I have a quick question. So I had heard about RapidWrite. I have never used it, frankly. But is there a tickle interface, or like how much, if I wanted to use it, how much effort is it? Do I have to write like a Java program where I have to learn data structures and pull information out of them using some APIs, or is there like a tickle console in Vivado that I can use RapidWrite with?
So the easiest way, if you're a Python user, you just say pip install RapidWrite. It's installed. Then you say import RapidWrite. Then it's in there. And you just start. So it is written in Java, but we have it set up so that you can access it. All the APIs are available in Python. So you can just say, if you want to load a DCP in Python, you just say, import design and then design.read checkpoint. You give it your file name, and boom, you've got a DCP object in your Python script.
Oh,
It's very, very easy. If you have any questions, I'm happy to answer them.
All right, let's thank Chris once again. That finishes our presentation section of the workshop. Let me connect the slide. All right. So, during this session, we heard from 5 experts ranging from, applications like streaming data, and machine learning, RF, and also a CAD expert. So I hope that everybody learned something new today, something interesting, how these, domain-specific architectures could be constructed, and hopefully gave some ideas to you for research. So in the next part, this poster session is our next part, which is supposed to be 30 minutes, but we're running late, so we'll squeeze that to 20 minutes. So we'll meet here back again at it's 10:53, so let's say 12:15 is when we'll start. And then we have this list of posters. The posters are all around the periphery of the room. Some of the posters, the presenters are not able to make it, unfortunately. We have 1, 2, 3, 4, 5, 6, 7 posters. And then a couple of them, the students had to leave because they had a flight, and we were just not, they didn't tell them in time to the schedule. So we have a few posters. Please go and interact with the presenters, and then let's resume back here again at 12. Oh, sorry. Yes. Yes,